Hello everyone, today we introduce a paper published at CVPR 2024 called Adaptive Multimodal Cross-Entropy Loss for Stereo Matching. Stereo matching is a task that aims to find dense correspondence between stereo image pairs. Then we can use the principle of similar triangles to calculate the depth of each pixel and reconstruct the 3D geometry. Currently, end-to-end stereo matching networks can be divided into three categories according to the aggregation method: 2D convolution-based, 3D convolution-based, and iterative optimization-based. In this work, we mainly focus on the 3D convolution-based methods. The 3D convolution-based stereo matching network outputs a disparity probability distribution for each pixel. Soft argmax is used to regress disparity from this distribution, and smooth L1 loss is employed for training. The main problem of L1 loss is that it lacks direct supervision of the cost volume and is thereby prone to overfitting. Moreover, soft argmax is based on the assumption that the output distributions are unimodal and centered on the ground truth, as shown in Figure A. But it is not always true, especially for the edge pixels with ambiguous depths. For multimodal output like Figure B, soft argmax estimates the disparity between the two models, which is known as the oversmoothing problem. When we use the oversmoothed disparity map to reconstruct the 3D point cloud, we find that there are a lot of bleeding artifacts in the point cloud. Another line of research treats stereo matching as a classification task, where the cross-entropy loss could be used. To guide the network to output unimodal distributions, researchers model the ground truth disparity with discrete Laplacian or Gaussian distributions. But we find that this type of method fails to suppress the multimodal outputs at the edge. We will show this in the subsequent experimental section. Furthermore, SME is proposed to obtain sharp disparity edges. SME first locates the disparity candidate with the maximum probability density, and then traverses left and right respectively until the probability stops decreasing, thereby determining the range of the dominant model for disparity estimation. However, this pixel-level winner-take-all strategy is sensitive to noises that can produce sharp and narrow models in the output distribution. Once the mode selection is wrong, SME will bring larger estimation errors and lead to misalignment artifacts. This picture shows some misalignment. For example, the upper left corner of the road sign is deformed, and some foreground green belts in the middle of the road are estimated to be on the background vehicles. We have explored the above issues. Our contributions can be summarized as follows. We propose an adaptive multimodal cross-entropy loss for training stereo networks. It can effectively guide the networks to learn clear distribution patterns and suppress outliers. We propose a dominant model disparity estimator that can obtain accurate results upon the multimodal outputs. Our method is general and can help the classic stereo networks regain highly competitive performance. GNet with our method ranks first on both the KITI 2015 and the KITI 2012 benchmarks among all published methods. Networks with our method exhibit excellent generalization performance, surpassing existing methods that specialize in cross-domain generalization. Please see the picture below. The point cloud reconstructed by our method has sharp edges and complete structure. Previously, we mentioned that using a unimodal distribution to model the ground truth distribution of stereo matching does not seem to work. In fact, edge pixels aggregate photometric information from multiple objects at different depths, implying that the intensities of edge pixels are inherently ambiguous. Intuitively speaking, the probability distributions of edge pixels should be composed of multiple models, with each corresponding to a specific depth. To this end, an adaptive multimodal ground truth modeling method is proposed. Our idea is to generate a separate Laplacian distribution for each potential depth on the edge pixels, and then fuse them together to construct a mixture of Laplacians. Specifically, for each pixel labeled with ground truth disparity, we consider a local window centered on it. The entire set of disparity values within the window is then divided into k-disjoint subsets by the db-scan clustering algorithm, with each cluster corresponding to a different potential depth. This clustering method offers the following advantages. First, there is no need to predefine the number of clusters. Second, k equal to 1 can be regarded as an indicator of non-edges. Third, it is robust for slanted planes with continuous but varying depths. Laplacian distribution is then employed for modeling each cluster. Local structural information is used to fuse the generated unimodal distributions. We take the cardinality of cluster as an indicator of the local structure. A smaller cardinality corresponds to a thinner structure, which should have smaller weight accordingly. The ground truth distribution of each pixel can then be modeled as the mixture of Laplacians. Finally, we use cross-entropy loss to supervise network training and use our generated multimodal probability distribution as ground truth. Stereo networks trained by cross-entropy loss often yield more multimodal outputs than the L1 loss, thereby a better disparity estimator is highly desired. SME alleviates the oversmoothing problem by aggregating disparities only within the most likely model, but still suffers from the misalignment artifacts caused by the erroneous model selection. In contrast to the unimodal loss, our new loss encourages the network to generate more multimodal patterns at the edge. Consequently, an enhanced disparity estimator becomes imperative to address the complexities introduced by our method. Furthermore, we propose our DME to solve this problem. Specifically, we split each model from the multimodal output and calculate their cumulative probability separately. Each model corresponds to a potential matching object with a specific depth, and the cumulative probability of the model reflects the matching possibility of that object. Therefore, we adopt an object-level winner-take-all strategy. That is, selecting the model with the maximum cumulative probability as the dominant model. We perform ablations on the scene flow dataset. The original PSM net trained with smooth L1 loss is taken as the baseline for comparison. To ensure fairness, all models are trained from scratch for 15 epochs on the training set and then validated on the test set. We verify the effectiveness of our proposed multimodal modeling and disparity estimator, and search for the optimal local window size. To have a deeper understanding of the change in the cost volume brought by our new loss, we count the proportions of pixels with different number of output patterns. As shown in the table, unimodal loss fails to suppress the multimodal outputs at the edge. Our multimodal loss yields more multimodals at the edge while resulting in low outliers. We also visualize the output of the network. We can observe that PSM net outputs little multimodal distributions but large disparity error. SME incurs misalignment artifacts from ambiguous distribution. Our loss outputs more easily distinguishable multimodal distributions than the unimodal one. We perform evaluation on scene flow and KD datasets. Our method significantly improves the performance of all of the baselines by simply changing the loss function and disparity estimator. GNet with our method achieves new state-of-the-art results on 2 KD benchmarks. Furthermore, we outperform those methods whose loss function contains a unimodal cross-entropy term by a large margin. To show our improvements more clearly, we convert the resulting disparity maps to point clouds. Our method dramatically improves the oversmoothing artifacts and can obtain the point clouds with precise edge structures. More accurate point clouds can be very beneficial for downstream tasks, such as pseudo-LiDAR-based 3D object detection. Besides the fine-tuning performance, generalization is also crucial for deploying networks in the real world. The generalization performance of the baselines is greatly enhanced by our method. Meanwhile, by guiding the networks to learn explicit multimodal patterns, our method shows superior performance than existing generalization-focused works on all 4 datasets. This proves that multimodal distribution is more in line with the nature of stereo matching. Thanks for watching. Welcome to scan the QR code below for more information.